Good morning, guys. So today, a few things. I want to talk a little bit more about partial fractions and work one or two problems there to completion, maybe some tougher ones. I want to show you some tricks that can be useful for speeding up the PFD process. And I also want to talk a little bit about the test and about the study guide. So I did post some instructions last week to Canvas, explaining exactly how to take the test, exactly how to wrap up the study guide, or how to hand that in. And I also posted a practice quiz. So let's see here. So if you come to our Canvas class and look at the announcements, if you click on this guy, there are some detailed instructions on how to complete the study guide and how to take exam 1. You need to read this. I know it's a big wall of text and it's, not the most fun thing in the world, but please read this carefully, pay attention to what's said here. Basically, the study guide, you're going to go into WebAssign and that's where you'll find the problems. But most of the credit is going to come from scans of your solutions. So you're going to write out your solutions in detail, neatly. I prefer one problem per page. That makes it the easiest possible way for me to grade it. And then you're going to upload your scans of those to Canvas, and they have to be PDFs. So I recommend the app Cam Scanner. That's worked great for me, but apparently the Notes app on iPhones is decent at this. Just make sure you have some app, and you can look in your app store for scanner apps. There's lots of free ones. Play around with them until you find one that is producing good quality PDFs that you can read. So you'll upload those to Canvas, and that is where your actual study guide score in the gradebook was going to come from. So the online portion there, the WebAssign, putting the correct answers into WebAssign, is not the study guide grade. That just counts towards the online homework. The actual study guide grade comes from the solutions that you upload. Exam 1 is going to run kind of similar. So the only difference is here you're going to need honor lock. So I've added an honor lock practice quiz. But during or at the start of class on Friday, you're going to want to come into our Canvas page and click on Honor Lock. It's over here. And then you'll go down to Exam 1 and hit Launch Proctoring. I set up a test quiz in Honor Lock so you can make sure that your computer is capable of running it. It will install the Honor Lock browser extension into Google Chrome. If you don't have it, you do need to use Chrome for this. So if you're using another browser like Safari on iOS or Firefox on Windows or Linux, please do download Google Chrome. You'll need that. And then within Chrome, you need the extension for Honor Lock. It'll automatically download the extension for you after asking you permission to do it, of course, if you open that in Chrome. So take the practice quiz in Honor Lock. Make sure that your computer is compatible with all of the Honor Lock stuff. If you run into any tech issues, please let me know. And then the exam itself is going to be in WebAssign. So when you go in there and click Launch Proctoring for the exam, you'll be redirected to WebAssign after a while. You'll solve the questions there, and as you solve them, you're going to write down your solutions, just like you did for the study guide, scan them, and upload them to Canvas. Scan and upload after you finish the test in WebAssign. So go through the test, writing down your solutions, submit the test in WebAssign, then take out your phone, scan your solutions, upload to Canvas. It's that simple. You must upload a solution for every single problem. The written work that you submit to Canvas is going to be worth at least as much as the WebAssign portion. Last semester, when I first started doing this online hybrid stuff, I was weighting them 50-50. So that means if you input the correct answer on WebAssign for a certain question, but you don't give me any work for it, you're only going to get 50% of the credit for that problem. If you were to do that for all the problems, you would get a 50% on the test. You'd fail the test. You don't want that to happen. So there's two reasons why we do this scan and upload shit. One, partial credit. You want that. Trust me, you want that. And then the other is so that I can verify that your work is actually your own, and I get a chance to critique your work, give you feedback. So I'll be writing comments on these and then scanning those comments in for you. Any questions on the mechanics here? What you must do, how to do it, what's expected? Not too bad, right? I mean, this online shit sucks, but we're making it work. If you have any ideas how to improve this this system, I would love to hear them. I'm definitely about that. But yeah, this is the thing that I've been doing for a bit now, and it's been working pretty well. If you run into any trouble with the HonorLock practice quiz, which is over here, all right, so you see you've got HonorLock practice quiz, and you guys will have different buttons over here. For me, it says results and settings, but you'll have a button that says launch proctoring. So that's how you take the practice quiz. There are no questions on the practice quiz. It's just the ID verification stuff. Yeah, so the study guide, this is a really good question. When would be a good time to talk about the study guide? Anytime. I'd love it, anytime. Come by office hours, send me an email, set up a meeting. You know, I've got 3 office hours this week, but only 2 of them are before the test. So if you're not free to come to today's office hour, I would recommend either planning to come to Wednesday's office hour, or ideally setting up a meeting with me on Tuesday. That way, because the office hours will likely be a little bit full. Because I tell everybody, please come bring shit to office hours so we can look it over together and talk about it. These tend to be busier office hours. So if you're nervous about it being busy or you can't come to today's office hour, please send me like an email or a Canvas message with a time tomorrow, Tuesday, that you would like to do that. Same for Thursday, right? If you can't come by Wednesday, or if you're worried about Wednesday being too busy, send me a time on Thursday you would like to meet up for an office hour. I do have a doctor's appointment tomorrow at 4:45 p.m. So just keep that in mind. I won't be able to meet anywhere between like 4:45 and 6 or 4:30 and 6. But aside from that, anytime today in office hours or tomorrow, I am free to meet with you guys to talk through your study guide, and I would love to do that. Strongly encourage it, right? It's a really good idea to show your professor some of what you're writing down before he grades what you're writing down. So it'd be a good idea. I would love to do that. And yeah, anytime tomorrow or Thursday, if you don't want to come to the office hour. Other questions? Hey, Lucas. All right, my wife just came downstairs and she's a little shy, so I'm gonna turn off my webcam and just leave the doc cam up. I hope you guys don't mind, so we can dig back into some problems. Okay. So this class is what it is. Today is the day it is. Things that we wanted to wrap up were see, we kind of already did this, talk about exam 1, study guide. Yeah. And the other thing to do is finish up our discussion on PFD, partial fraction decomposition. Is there anything I'm missing here? If you do have any testing accommodations, I've spoken to a few people already. I wouldn't mind a quick Canvas message just to remind me. So if you have testing accommodations through the DRC or are close to getting those or think that those might apply, do send me just a quick follow-up message, even if we've already talked about it on Canvas. That way I can go in and double check that everybody has exactly what they should have. So if you have testing accommodations, send me a message reminding me exactly what those are. And I will make sure to put them in the testing parameters when I set up exam 1 in WebAssign. So let's return then to section 7.4. I want to show you a trick for finding the coefficients in the partial fraction expansions quickly in the nice case. Sure, Ryan. Yeah, we can do that in an office hour. Or we could do it here quickly after class. Either one is fine. So recall, partial fractions is an algebra process for splitting up proper and remember what we mean by proper, degree of the top is strictly less than the degree of the bottom, is a process for splitting up proper rational functions. We do it to help solve integrals. At least right now. But later, when we talk about sequences in series, we're going to do partial fractions to help us find series representations. And in other settings, you'll do partial fractions to find inverse Laplace transforms, all sorts of other good stuff. Well, sorry. Is it okay if I leave the video on? You want me to leave it off? I'll leave it off. Sometimes the gestures and stuff are useful. That's okay. All right, so partial fractions is an algebra process for splitting up proper rational functions. Proper means degree of the top is strictly less than the degree of the bottom. We do it, at least right now, to help solve integrals. So an example of a problem that we can work with partial fractions that we haven't been able to work in the past is something like 1 over x cubed minus x. It's an indefinite integral. And the thing we're integrating, the integrand, is a rational function. We can do these with definite integrals also. The indefiniteness doesn't matter. The first step is to come off to the side and just write down your function. You can factor the top and the bottom. Here the top is just 1, so I don't have to worry about factoring it. The bottom factors as x times x squared minus 1, which is x times x minus 1 times x plus 1. We check that it's proper. We cancel any factors top to bottom that we could cancel. You know, all the standard algebra rational function stuff that you want to do before you get started. And then we move to the PFD setup. Here, the PFD setup is really nice because each of these, this denominator factored into distinct linear factors. It would be a mistake to stop here and say, oh, well, this is a quadratic factor, so I have to do that weird quadratic thing, because he is not irreducible. He factors. So remember, factor everything as far down as you can before you get started with the PFD. Now my PFD setup, which is the only thing that you have to memorize for this really, is going to be nice and simple here because we have distinct linear factors. If we had repeated factors or irreducible quadratic factors, this setup would be nasty or nastier. But here it's not bad at all. Each one of those distinct linear factors gets his own term, and it looks like this. The trick I wanted to show you today will allow you to calculate A, B, and C much faster. You no longer need to go through and equate coefficients the way we had been and set up a big linear system if you're in this nice case. So I'll show you what I mean. It's called the Heaviside trick, or some people call it the cover-up method. I'm going to multiply, cross-multiply, and cancel everything. All right, so I'm going to multiply by x times x minus 1 times x plus 1. This gives me the left-hand side. I'll just have my numerator, which is 1, equals. When I distribute x times x minus 1 times x plus 1 over the right-hand side, here the x's cancel, and I get a times x minus 1 times x plus 1. Plus here I get b times the x minus 1's cancel, so I'll have x plus 1 times x. And here the x plus 1's cancel, so I'll have c times x minus 1 times x. So to go from this line to this line, I'm just multiplying through by this denominator. Over on the left-hand side, everything cancels. On the right-hand side, one piece cancels per term there. Here's the trick. If I plug x equals 0 into this equation, something cool happens. because both this piece and this piece have x as a factor, when I plug in x equals 0, those terms will both go away. This would be b times 1 times 0, which is definitely 0. This would be c times -1 times 0, which is also 0. So if I plug in x equals 0, I get 1 equals a times 0 minus 1 times 0 plus 1. That's the same as saying 1 equals negative a, which means a equals -1. And just like that, without multiplying everything out and collecting coefficients and solving a linear system, I get a. This is called the Heaviside trick. If I plug in x equals 1, this guy will vanish and this guy will vanish. So I'll get b out. If I plug in x equals 1, then my equation above becomes 1 equals a times 0 times 2, or 2 times 0 times a. Either way, this term is 0. This term would be b times 2 times 1, so that's 2b. And this term would be c times 0, which is 0. So in other words, b is 1/2. And if I plug x equals -1 into this expression, then this piece is 0, so the a's go away. This piece is 0, so the b's go away, and I'll get c out. So I'd have 1, this 1 equals c times -2 times -1. In other words, 1 equals 2c, so c is also 1/2. Isn't that slick? So you're able to get your coefficients, you're able to get these numbers a, b, and c from your PFD setup really, really quickly using this trick, which is called the Heaviside method. MIT a few years ago released a little paper justifying exactly why this works. Really, when you're plugging in, we're actually taking a limit. The original function isn't defined for those particular values. But the simplified form after clearing all the denominators is defined there, and so it all works out nicely. The numbers that you're going to plug in for x, I want to first be clear about this. You can plug whatever the hell you want in for x here. But the numbers that will be most useful are the numbers that make these factors equal to 0. Because of the way the algebra works, when you distribute this term, when you cross multiply and distribute, all except for one of the factors will cancel in each of the simple terms. That is, each of the case 1 terms that came from non-repeated linear factors, which means that the other two pieces will remain. So if I want to find a, I plug in whatever will make these two guys 0. And since they both contain this factor x, I plug in x equals 0. That makes these two go away, and I'm just left with the a stuff. If I want to get b, I plug in whatever will make these two 0. Since both of them contain a factor of x minus 1, I need to plug in 1 to get b. And then I get this equation, because these are both 0, and this becomes b times 2. Similarly, to find c, I plug in whatever makes the other two guys 0. Each of them has a factor of x plus 1. That tells me, okay, plug in -1. In other words, to get each coefficient here, you plug in the thing that makes his denominator 0 in the original PFD setup. So to get a, I plugged in x equals 0. To get b, I plugged in x equals 1, because that's what makes this denominator 0. And to get c, I plugged in x equals -1, because that's what makes his denominator 0. But you have to plug it in into this line. Right? You have to plug it in into the cleared line, because this is not defined at those x values. This is. So it's a very neat trick. It only works to recover these case 1 terms. If you had a repeated factor or an irreducible quadratic factor, you won't be able to get these guys like that. But this allows us to set up a strategy. If you do have a complicated PFD problem, get the easy guys first using the Heaviside method. Then expand everything out and go after the harder to find terms. And I'll do an example like that. But before we do that, let's finish this problem. So here we said my function 1 over x cubed minus x should be equal to a over x, which was negative 1 over x, plus b over x minus 1, that's 1/2 over x minus 1, plus c over x plus 1, that's 1/2 over x plus 1. So the integral of my function is equal to the integral of that function. And the magic is that now I can split this integral up and handle each little piece on its own. So that first guy, that's negative integral dx over x. The second guy is plus 1/2 integral dx over x minus 1. And this last guy is plus 1/2 integral dx over x plus 1. This first integral is straight up natural log. This guy requires a little u substitution, and then he will become a natural log. And this guy also requires a little u substitution, and he will become a natural log. Since those are tiny little substitutions, ones where du is equal to dx, I'm not even going to bother writing them. And hopefully you are getting to a place with those little micro u subs where you can do them in your head like this. But if not, that's okay. Just go off to the side and do them. This is how it will come out. I do have a warning. When I cover this section, some students do have a tendency to develop the following belief. Some people see the integral of 1 over something and always assume it's going to be a natural log. That's not true. It's just not, unless f of x is of the form x plus b. That's it. That's the only time that shit works. Right? So if your denominator is more complicated than just x plus or minus some number, then you can't just say the integral 1 over f is going to be a natural log. Please don't fall into this trap. Common trap to fall into, because you start seeing so many things like this show up, you start thinking, oh, everything works that way, but it's not true. I just want to insert that as a warning. The only functions for which this is true are linear functions whose slope is 1. All right. So that's the Heaviside method. That's the trick that makes PFD go faster. Okay. Questions on the Heaviside method? Everybody comfy with what we did here? So some of the ways that this can become a bit more complicated, if your rational function is not proper, then you need to do some long division at the start. We haven't done any of that ourselves yet. Also, I'd like to show you how to mix this method with the method of undetermined coefficients that we were using last week. So polynomial long division, you could be forgiven if you don't remember it, but you need to remember it. So I'm going to grab an example. Sorry, my legs are sore. I groan and grumble every time I got to move. Grab an example from your textbook. Shit. All right. Do we have any repeated factors here? We do. All right. I got a big scary example. Get ready. We are going to integrate. This is, yeah, improper. Okay, good. You're going to integrate x to the 4 minus 2x squared. Really? Squared? Yeah, okay. plus 4x plus 1 all over x cubed minus x squared minus x plus 1 dx. So here's our big, scary end of 7.4 problem. We notice a few things. First, the thing I'm trying to integrate is a rational function. The top and bottom are both polynomials. Second, it is not a proper rational function. The degree of the numerator is larger than the degree of the denominator. Even if they were equal, this would be improper. So we need to long divide the top by the bottom. Before we do any of that, though, you might consider factoring. I don't see at a glance an easy way to factor this. The numerator is tricky. The denominator, I think I could probably factor using a trick, and I'll show you that after we do the long division. So first, let's go ahead and knock out that long division. We know that this is an improper rational function. That's where we got to start. So the improper rational function tells us we're going to long divide, then PFD. But we got to long divide first. This long division is a little bit gnarly. Here's how it works. You write the denominator, and then next to it over here, you write the numerator, making sure to insert any missing terms. Notice there is no x cubed term there. So I need to insert it as a 0x cubed. So I write x to the 4 plus 0x cubed minus 2x squared plus 4x plus 1. Now, if you took pre-calc with me, then I beat polynomial division into your heads with a brick. But if you took it with someone else, you may have never even seen this. It looks a lot like regular long division, right? I'm using the regular long division symbol here. And the way you get this done is just by thinking about the lead terms. So you think just about this term and this term. So by what must I multiply x cubed in order to get x to the 4? Well, x times x cubed would be x to the 4. So I begin by writing an x up here. Then I take this x and I distribute it to each term here, and I write down what I get here underneath. Again, just like your regular long division algorithm with numbers. X times x cubed is x to the 4. X times negative x squared is negative x cubed. X times negative x is negative x squared. X times 1 is x. And then I subtract the whole row from the row above. X to the 4 minus x to the 4, that's 0. 0x cubed minus negative x cubed is 1x cubed. Negative 2x squared minus negative x squared is negative 2x squared plus x squared. That's negative 1x squared. 4x minus x is 3x. And 1 minus 0, the constant term here is 0, is 1. Or you can think of it as the 1 just comes down. That's one loop of this algorithm. Now you're just going to rinse and repeat. So you're going to apply that same rule to this row. So what must I multiply this by? The first terms only. What must I multiply x cubed by in order to get x cubed? 1. So up here goes a plus 1. And then I distribute this 1 to every term here, and I write that down here. So 1 times x cubed, that's x cubed. 1 times negative x squared, that's negative x squared. 1 times negative x, that's negative x. And 1 times 1 is 1. And now I subtract this whole row from that whole row. X cubed minus x cubed is 0. Negative x squared minus negative x squared, that's also 0. 3x minus negative x, that's 4x. And 1 minus 1 is 0. And now that the degree of this is strictly less than the degree of this, I stop my algorithm. There is no polynomial I can multiply x cubed by in order to get 4x. So I stop. Once this power is smaller than this power, stop. What this tells us is that my function, x to the 4 minus 2x squared plus 4x plus 1 over x cubed minus x squared minus x plus 1, this is equal to x plus 1 plus this remainder over this denominator. So plus 4x over x cubed minus x squared minus x plus 1. So this long division gets us here. So that's our first step. Notice the result. You get a polynomial piece plus a proper rational function piece. This polynomial piece will be easy to integrate. This is going to require PFD. So now I come off to the side and I do my PFD just for this piece. So now we set that up. That means I'm going to need to factor the denominator. If I factor an x squared out from here, then I'll be left with x minus 1. So let me write it like this. I'm going to bring x squared from those first two pieces, and that will give me x minus 1. And then I'm going to bring a minus 1 from that second piece. That will also give me an x minus 1. So this is like 4x over, I'm factoring by grouping the thing in the bottom. I have x minus 1 that I can bring out on the right, and what's left will be x squared minus 1. So this is factoring the denominator by grouping. From the first two pieces, x cubed minus x squared, I factored an x squared. I did that because the bottom looked like something that could be factored by grouping. And indeed, if I bring a negative 1 out from the latter two pieces, that will also become an x minus 1. So since I was able to see ahead that if I do this and if I do this, these two pieces will match, that tells me I can factor it like this. And then this piece factors as a difference of squares. That's x plus 1 times x minus 1 times x minus 1. But I shouldn't leave it like that because this is a repeated factor. I should write that as 4x over x plus 1 times x minus 1 quantity squared. Questions on the algebra so far? Technically, so far, this is all pre-calculus, but I know pre-calculus classes vary quite a bit. So we've got our long division, and then our factoring the denominator. These are both two important skills. Yeah, so factoring by grouping is a sneaky trick. So I had x cubed minus x squared minus x plus 1. If I want to factor by grouping, what I do is I think about this as a piece and this as a piece. And I ask, do those pieces have any shared factors? In this piece, I see what looks like a factor of x minus 1 hiding. And in this piece, I see what looks like a factor of x minus 1 hiding. So I try to extract that factor from each piece. To make an x minus 1 show up here, I factor an x squared. And to make an x minus 1 show up here, I factor a negative 1. And that gives me this common factor of x minus 1 between these two pieces that are being subtracted. So I can factor the x minus 1 out. This is this x squared, this is this 1. And on the right, I have the x minus 1 that I've pulled out from each of them. So think of this as like x squared times a minus 1 times a. I can pull the a out, and I get x squared minus 1 times a. Only here a is the polynomial factor x minus 1. That's kind of what's going on. And then the x squared minus 1, he factors himself as a difference of squares. So altogether, I end up with x plus 1 times x minus 1 quantity squared. It's actually the same trick you use at the end of the AC method for factoring quadratics. If you learned how to factor quadratics that way, the superior way, I claim. But it can be useful in factoring higher order polynomials as well. So I know it's definitely possible that you guys haven't seen any, but at no point have you seen a cubic polynomial factored by grouping, but this works great. If you don't remember this, your rational roots theorem will work also. You can test all of your p's over q's one at a time until you find something that works, but that takes so long that I always look to try and factor by grouping if I can. So that brings us back here. I will try to remember to post a little something under the Canvas review module on factoring by grouping. So now it's time for the PFD setup. The only piece that needs the PFD is this piece. So I take my 4x over x plus 1 times x minus 1 squared, and I write that as a over x plus 1 plus b over x minus 1 plus c over x minus 1 squared. Remember, repeated factors in the bottom, you have to build up to them in your setup. You can't just have the x minus 1 squared term. You also need the x minus 1 term. It's just how the algebra works. Coming from a field of math called linear algebra, asking what sort of combinations of things can lead to certain things. I'll clear through multiplying out, get rid of my denominators. So I multiply by x plus 1 times x minus 1 squared. The left-hand side just becomes 4x. The right-hand side, when I distribute everything, is going to be a times x minus 1 quantity squared plus b times x plus 1 x minus 1. So here this x minus 1 cancels one of the x minus 1 factors, and then plus c times x plus 1. So in this term, the x plus 1 cancels, both x minus 1 stay. In this term, one of the x minus 1's cancels, the other x minus 1 stays, and the x plus 1 stays. And in this term, both of the x minus 1's cancel, only the x plus 1 stays. Now I use my Heaviside method. Heaviside method won't get me everything, but it will get me some things, and I should use it to get whatever I can out before I move on from here. So if I plug x equals 1, this term will drop out, and this term will drop out, and I will get this guy. So my left-hand side will be 4 times 1. My right-hand side will be 0a plus 0b plus 2c. So c is equal to 4 over 2, that's 2. If I plug x equals -1, then this would be -4 equals, let's see, -1 minus 1 is -2, but when I square that, I get +4, so this is 4a. This would be 0 times b, and this would be 0 times c, so this is all I get. And that tells me that a is equal to -4 over 4, that's -1. So I'm able to get 2 of these numbers using the Heaviside method. There is no other number I could plug in here to make things equal 0, right? 1 makes the x minus 1 factor 0. -1 makes the x plus 1 factor 0. But there's nothing else that's super nice like that. From here you have 2 choices. First, you could multiply all of this out, collect your like terms, and equate coefficients. So Caesar asks why -4, and while we're there we should probably also ask why +4 here. I'm plugging into this equation. So when I plug x equals 1, the left-hand side becomes 4, and the right-hand side becomes 2c. When I plug in -1, the left-hand side becomes 4 times -1 is -4, and the right-hand side, everything goes away except for the a, which is 4a. So you got to make sure you pay attention to the left-hand side as well as the right-hand side when you go to plug in. So now I'm going to update that equation. I now have 4x equals a times x minus 1 squared. Well, that's -1 times x minus 1 squared plus b times x plus 1 x minus 1 plus c is 2 times x plus 1. So this is my updated denominator cleared fraction where I plug in the values of a and c that I already found. You could go ahead and plug in any other number you wanted for x, and that would let you find b. But what if I had more than one coefficient left? What if I also had like e, f, and g that I still needed to find, that I still couldn't get using the Heaviside method because they came from case 2, 3, or 4 factors in the denominator? Then I would need to multiply everything out and collect my like terms. So let's go ahead and do it like that, just for practice. This is -1 times x squared minus 2x plus 1 plus b times x squared minus 1 plus 2x plus 2, which is the same as -x squared plus 2x minus 1 plus bx squared minus b plus 2x plus 2. And now I put all my x's together, my x squareds together, and so on. X squared terms are here and here. So I have b minus 1 x squared. X terms, I've got plus 2 of them here, plus 2 of them here. That's plus 4x. Constant terms, I have minus 1 minus b plus 2. So minus 1 and plus 2 is 1, and minus b. So I've got plus 1 minus b for my constant terms. And my right-hand side is 4x. That's 0x squared plus 4x plus 0. Okay. So now we're going to do the same thing we were doing last Friday, where I take the coefficient of x squared on the left, and I set it equal to the coefficient of x squared on the right. I could take the linear coefficient on the left and set it equal to the linear coefficient on the right, but I don't actually learn anything there. I just get 4 equals 4. And I can take the constant term on the left and set it equal to the constant term on the right. That gives me the following system of equations. And if I needed to find more coefficients, I would just continue solving this system. I get b minus 1 equals 0, 4 equals 4, and 1 minus b equals 0. This is not a tricky system to solve. Clearly b is equal to 1. But if I had other coefficients that I hadn't found yet, like E, F, G, H, I, like you've seen in those really nasty setups, we would be able to get them by solving this resulting linear system. Questions about where this system came from? The 4 equals 4, each of these equations came from setting the coefficient on the left equal to the coefficient on the right. So on the left-hand side, the coefficient of x squared was 0. On the right-hand side, the coefficient of x squared is b minus 1. So b minus 1 has to be equal to 0. On the left-hand side, the coefficient of x is 4. On the right-hand side, the coefficient of x is 4. That's where the 4 equals 4 line came from. And then the last equation came from setting the constant term on the left equal to the constant term on the right. Constant term on the left is 0. Constant term on the right is 1 minus b. This is what's called an overdetermined system. I don't know how much you guys talked about systems in your pre-calculus class, but I only have one unknown. I have 3 equations, so this is an easy system to solve. But if I had more unknowns, like constants E, F, G, H, whatever, then those would show up here, and you would use whatever methods you have for solving linear systems: substitution, elimination, matrices, whatever you remember from your pre-calculus class and you want to use, you would use it there. But since this one is easy, we just get b equals 1. We already had a and c. So finally, we know that 4x over x plus 1 times x minus 1 squared is equal to a over x plus 1, that's negative 1 over x plus 1, plus b over x minus 1, that's 1 over x minus 1, plus c over x minus 1 squared, and c was 2, so it's 2 over x minus 1 squared, that's c. And now and only now do I come back and solve my integral. So my integral was this thing. And we said that that function is really equal to this function. So let me recap. So what do we have all together? We have my integral x to the 4 minus 2x squared plus 4x plus 1 over x cubed minus x squared minus x plus 1 dx. We said by long division, that's equal to, what was it, x plus 1. Right, this was our output from the long division, so I'm just going to put this in. plus 4x over x plus 1 times x minus 1 squared. And then by PFD, I can expand this part. That's equal to the integral of x plus 1 plus, and then this part is this, which is this by PFD. So plus negative 1 over x plus 1 plus 1 over x minus 1 plus 2 over x minus 1 squared dx. That is the fully expanded form of that rational function. Bit of a mess, but we expected that. The degree of the top was 4, the degree of the bottom was 3. This integral looked terrifying at the start. But we did some long division, then some PFD, and we got it down to this. X plus 1 integrates to x squared over 2 plus x. This is minus ln absolute x plus 1 plus ln absolute x minus 1 plus 2 times the integral of 1 over x minus 1 squared dx. So each of those is a little micro u sub. This last guy, though, he's a bit different than the others, so I wanted to ask you, what do I do for him? Rather than just writing down the answer there, how do I integrate that? Who can help me with this? Yeah, it's a little substitution. If I make the substitution z equals x minus 1, then dz is dx. And this becomes 2 integral 1 over z squared dz, which is integral z to the negative 2 dz, which is 2 times z to the negative 1 divided by negative 1, or negative 2 over z, plus a constant, I guess I should say. I'll just write it like that for now. So finally, we get, right, this is the side work for this, x squared over 2 plus x minus ln abs x plus 1 plus ln abs x minus 1 plus, minus 2 over x minus 1 plus c. So this right here is your final answer. Very good. All right. Good news, this is about as scary as these get. Bad news, you know, scary problems like this exist. Good news, on a test, my problems will be designed to ask you to do one of these things at a time. This problem makes you do all that shit together. So I might give you the final factored form like this after the long division, after all that stuff, and ask you to do everything from here. Or I might give you the improper thing and ask you to take me from here to here. Any of those would be a good exam question, but doing all of this stuff at once is too much to put on a single question. So if you're thinking, holy shit, this exam's going to take 10,000 years, don't panic. It's not going to be 10 questions like this. It's going to be 10 questions, each of which looks like one of these big steps. So the long division step, the PFD step, the integration step. Each of those would be an appropriate exam level question. In practice, I will probably find 1 or 2 small PFD problems to put on your test, rather than a big PFD problem like this. What we haven't seen is how the Heaviside method interacts with irreducible quadratic factors. It goes the same way as it does with repeated factors. You get everything out that you can using the Heaviside method, and then you resort to the method of undetermined coefficients for whatever remains. So here, Heaviside was able to give us these 2. We still needed to get B, so we used the method of undetermined coefficients and set up this linear system to find B. The same thing would have been true if we had an irreducible quadratic factor. We wouldn't be able to get those coefficients out using the Heaviside method. So after we got everything else out, we would cross multiply and set up our system. There are some problems in your homework that will give you some practice with that. So I'm not terribly worried. I think with a little bit of practice, you guys will become masters at this. The trick to being good at PFD is keeping your shit organized. And you'll find that that's the case with a lot of the stuff in Calc 2 because it's very procedural. Making sure you write things down neatly and just follow the steps one at a time will always get you there. If you try to skip steps, it will bite you. So take your time, go slow, and make sure you're doing things correctly. That way you don't have to do them a second or third time. There's a saying, this is incredibly nerdy, I used to race RC cars, and there's a saying there called slow is fast. It's very simple, because if you go fast, you crash. And it's much, much faster to get around the track without crashing, even if that means going a little bit slower, than trying to hammer the throttle the whole time and crash. So go slow. Slow is fast. Last call for questions on this problem, any one of these steps. I like that. Slow is smooth, smooth is fast. Yeah, very good. Yeah, where have I heard that before? Wisely and slow, they stumble that run fast. I don't, what is that from, Simon? I don't remember. Shakespeare. Oh, okay. Oh, yeah. That's the priest to Juliet, right? Yeah. Good shit. All right, thank you. This has been fun and more literary than I expected. I do have more shit to talk about today before we kind of dismiss learning new stuff and move entirely towards focusing on the exam. So Wednesday will be all practice for the exam. You guys, I want you to bring problems that you have from the study guide, problems that you have from the homework. We're going to try and jam through as many of those as we can in class on Wednesday to get everybody amped and ready for the test and fill in all those gaps. But there's one last little bit of theoretical discussion. And for this, I'm actually going to bring up your textbook because it's more about reading than it is about writing. Oh, and I'll use the digital version rather than the physical version. Do I have a copy of that here? Yeah, Calculus 8th edition. Okay. So the last section we need to talk about after this is this. This is the last section on exam 1. The good news is there's nothing new here. 7.5 doesn't have anything new. But what it does have is combinations of all the shit from the previous 4 sections. This table you should probably know, maybe with the exception of the bottom 2 rows. I would make sure that you know 1 through 18 here. And I think most of these are things that you'll know. I guess you could probably also skip 15 and 16 because we don't talk a lot about hyperbolic trig functions. I will tell you from time to time when we run into something cool involving them, but I will not hold you responsible for them. So make sure you know 1 through 14. And then 17 and 18, these are fun things to prove that will save you a dickload of time. Consider it, all right? This is not a hard proof. It's trig sub. We actually did this one. I don't know if you guys remember. You substitute x equals a tan theta, and you'll get this general result out. which tells you really quickly how to integrate not just 1 over x squared plus 1, but also 1 over x squared plus 2, 1 over x squared plus 3, 1 over x squared plus 4. Definitely make sure you know 1 through 14. I strongly recommend proving 17 and 18 for yourselves. Don't worry about 15, 16, or 19 and 20, although if you are bored or looking for an extra challenge, going through the proofs of 19 and 20 is a good exercise in trig sub. This one is actually a PFD problem. This one is trig sub. The purpose of 7.5 is to kind of talk a little bit high level about how you want to attack an integration problem in general. So of course, if your integral is just one of these, write down the answer and call it a day. If it's not, what should you do? So if I'm handed an integral and I don't immediately see what to do with it, I look for some algebra. Can I clean the thing up? Can I write my thing as a polynomial or as a sum of power functions? Is there any way to do some algebra to make my integrand nicer? A good example of a problem like this is something that you may have seen back at the end of Calc 1. So I'll do a little bit of writing here. (7.5) strategy for integration 1. So simplify your integrand into a polynomial or a sum of power functions or whatever. You know, if you're dealing with trig functions, simplify into nicer trig functions. Do some algebra to make your life easier if you can. For example, your book has an example there, but I like this one better. If I gave you this, you might have a hard time seeing what to do. It's maybe not obvious. There's a square root, so maybe trig sub, but the thing under the square root doesn't look trig subby, but it's definitely not something I know an antiderivative for right away. However, if you write it as x squared over root x minus 2x over root x, and then simplify each of those pieces, x squared over root x, that's x to the 2 over x to the 1/2, that's x to the 2 minus 1/2, which is x to the 3/2, and 2x over root x, that's 2x to the 1/2. Now you can integrate. That would be x to the 3/2 plus 1 is x to the 5/2, so 2x to the 5/2 over 5 minus x to the 1/2. 1/2 plus 3 is 3/2, so this would be 4x to the 3/2 over 3 plus c. So do algebra wherever you can. All right, if you can simplify your integrand into something you know how to integrate, do that. Do that before trying any other tricks. Okay, I'm going to flip back to the book here so you can see the book's example really quick. Any questions on the example I did here? Pretty straightforward shit. So the book's example here involves distributing a square root of x and rewriting this as a power function, or cleaning up a ratio of tangents and secants into a sine function, that sort of thing. Next, look for a substitution. If you see an obvious u sub, for example, sine theta over cos cubed theta d theta. Here you would want to sub u or z equals cos theta. So that you get negative 1 over z cubed dz, which is negative integral z to the negative 3 dz, which is negative z to the negative 2 over negative 2 plus c, which is negative 1, oh, actually positive at the end of the day, positive 1 over 2 times cos squared theta plus c. If you see an obvious u sub, go for it. That means if you see a composite function and the necessary piece for the differential, go for it. Without the sine theta upstairs, this is not an obvious substitution. If you tried to make this substitution without the sine theta upstairs, it will be very hard. So look around for a composite function that has the derivative of the inner floating around, an obvious u sub. Think 5.5. The book has some examples here, like in this guy. The obvious substitution is for the denominator. I should substitute u or z equals x squared minus 1. If there is no obvious substitution and there is no obvious algebraic maneuvers, then you're going to want to think about the sections we've gone over, right? IBP, trig integrals, trig sub, partial fractions. Is this something that we can treat using the trig integral techniques that we learned in section 7.2? If you've got pretty much any mess of trig functions, you can always rewrite them as powers of sine and powers of cosine, powers of secant and powers of tangent, or cotangent cosecant. And then you can handle those, because all of those we know how to handle. The worst case here requires a little bit of IBP. Sure. Yeah. Here we go. We want to stay here just a second longer. Yeah, no problem. So maybe while you're doing that, I will, we could actually simplify this a tiny bit further as 1/2 secant squared theta plus c. And that's how I would write that if it were me. So yeah, try to do some algebra. If there's no obvious algebra to be done, look for an obvious u sub, an obvious z sub. But plenty of times you won't have that either. See a third. So when we say classify according to form, we're going to mean think about 7.1 through 7.4. Is this a trig integral? What about, does it look trig subby? Is it a rational function? All those things. If not this, maybe some, does it look like something we could come out with IBP? Rational, this would mean we're going to do some PFD. So classify according to form. Not every rational function should be integrated with PFD. Sometimes a simple substitution will work. Sometimes trig sub is the way to go. And the way you get comfy making those choices is by solving lots and lots of problems. So the shape of the integrand will start to inform your strategic decisions once you have practiced enough. Now might be a decent time to tell you guys that Santa Fe College actually has a math team. Some of your classmates are on the math team. And one of the things that we've been doing over the last year, the coronavirus kind of crapped on us because all of our competitions were canceled, is building a team of integrators. a team of students that I can send to integration competitions. There's one in town called the UF Integration B, and Santa Fe students are allowed to participate in that. It was canceled this year because of the coronavirus, and it also happened to be at the same time as the Math Olympics, so we're going to have a hard time sending a full team. But if you enjoy integrating, if these problems are problems that make you happy when you solve them, consider joining the math team, because I always need more integrators. All right, I am going to move to the next row here. So if we continue down in the textbook's little strategic discussion after we have classified our integrand according to form. Sorry. So they've got a few specific hints here. Are they trig functions? If yes, do that stuff. Are they rational functions? Consider using PFD. If none of those, does this look like something we could do with integration by parts? That is it like a polynomial times an exponential or trig function? Does it have logs in it? So if so, try setting up your Lipet rule and take a look at the integration by parts. It might not be bad. And also, does it look trig subby, right? Does it look like something we want to use a trigonometric substitution on? You can also occasionally make what are called rationalizing substitutions. We haven't seen a lot of this, and you don't expect to see a lot of this, but every now and then, if you have a weird root of a linear function, you can get away with a substitution like this. Not always, sometimes. That's pretty much it. So that's all the stuff that's introduced in 7.5. We don't use computer algebra systems or any of that. Where is it? Tables, integrals. Sorry, I skipped accidentally to the next section. So this is it. Right? They go on to solve a few examples here. And I would be happy to do one or two of these with you. But the most important thing is that you're starting to develop some intuition for what method to use. If you run all the way through these things and nothing has helped yet, they say just try again. So maybe you didn't look hard enough for that obvious substitution. Maybe you didn't look hard enough for that algebraic simplification. So they're saying if you don't see what to do after having run through those things, try some substitution, even if there isn't an obvious one. See if there's one you can make go. We've seen that sometimes, where we want to do a substitution, but we don't have the necessary term for the differential, but we're able to solve our original expression for x and then make the differential term go. So try a less obvious substitution. If there's still nothing there, you don't see anything like that, integration by parts is badass. It's a tank. It can do so much stuff. So if your function, especially if you have like an inverse function or whatever reason you think by parts might be useful, give it a shot. It couldn't hurt to try writing down one or two IBP tables and see if the integral you get out is an improvement upon the original problem. And then they list this lastly, but really this is the first thing I would think about. See if there's some more clever algebra you could do. Like this guy, you saw him in one of the homeworks. This is a multiply by the conjugate trick. And it's not too hard. Saying IBP is like the Calc 2 version of the quadratic formula might be a little bit overkill, but IBP is definitely a powerful technique. It will solve a lot of problems. It won't solve all of them, but it will solve a lot of them. And then the last little bits of advice here, and I recommend that you go through and you read these carefully. Try to relate this problem to something else. Like, does this look at all similar to something else you've done? We've seen the tangent squared secant integral, but if we hadn't before, we could reduce it into the secant cubed integral. And it turns out that even powers of tangent times odd powers of secant can always be turned into just straight odd powers of secant. Stuff like that. All right, so see if you can connect the problem you're working on to a problem you've worked in the past. And then this part C down here is a bit of a cop-out. It just says use several methods. So, okay, you made a substitution, but it still looks hard. Try some other shit. But try that shit from the substituted integral. Or you did IBP, but it still looks hard. Maybe try a substitution in the integral you got out from IBP. So in other words, don't give up. Many of these are not one-step problems. Many of them are 2, 3, 4-step problems. So if one attack doesn't yield the result immediately, ask yourself, are things getting better? If things are getting better, you should continue down that path. Yes, it's possible that that path doesn't lead to the solution, but you'll never know unless you really try. So you got to push a little bit harder than you might think before you start seeing that shining light at the end. All right. So Fernando asks, are there rules on the tries in the study guide? If I set it up how I normally do, then yeah, you should have, I think the WebAssign max limit is actually 55. So I'm not able to set it to unlimited submission attempts, but I can set it to 55, and I believe that's what I did. So you should have effectively infinitely many tries. If 55 tries isn't enough to get it right, then something is horribly wrong. But I will double check because sometimes I do forget to modify those settings. So let me look. And then the rest of class, there's not a whole lot. Yeah, JP's press. So you're good to go. You got 55 tries on each of those problems. Remember to write out your solutions, and you're going to have to scan and upload those on Friday before you begin the test. We got a couple minutes left here, so if you guys would like to work one more problem, I'd be happy to work anything from the homework to the study guide. Is there anything that's been driving us crazy lately? Okay, Gustavo, we will do that. The exam one study guide in WebAssign is the study guide. So it's not the exam itself. You can think of it as practice, sort of. That's the idea. But it's the thing that the syllabus discusses as the study guide. Just make sure you read the Canvas announcement about it. That way you'll understand exactly where the grade is going to come from. So please read that Canvas announcement. All right, let's take a look. Gustavo wants to see number 14 from the homework. I assume that's homework 5, the more recent one. So let's pop that up. Yeah, this is good shit. All right, x to the 4 over x minus 1. Can anyone advise? What do we do? So this is a rational function. There might be some PFD in our future, but yeah, we need to long divide because the degree of the top is bigger than the degree of the bottom. So I write my denominator here, x to the 4 plus 0x cubed plus 0x squared plus 0x plus 0 over here. Remember, we always insert those missing terms. X, I pay attention just to the lead term. So what times this lead term equals this lead term? That's x cubed. And then when I distribute that x cubed, I will get x to the 4 minus x cubed. I subtract. Oh, sorry, x to the 4. I said it but wrote it wrong. So x to the 4 minus x to the 4 is 0. 0x cubed minus negative x cubed, that's positive x cubed. And then all of these come along for the ride, 0x squared plus 0x plus 0. To get this to turn into this, I need to hit it with an x squared. And when I distribute the x squared over this, I get x cubed minus x squared, and then I subtract the whole row. X cubed minus x cubed is 0. 0x squared minus negative x squared, that's positive x squared, and then the other 0x plus 0 terms come along. To turn this into this, I need to hit it with an x. X times x minus 1 is x squared minus x. Subtract. This is 0. This is x plus 0. To get this into this, I need a 1. And that will give me x minus 1. And then I subtract. and this gives me a 1. Now the degree of this is strictly less than the degree of this. So in other words, what I've discovered here is that x to the 4 over x minus 1 is really x cubed plus x squared plus x plus 1 plus 1 over x minus 1. This remainder over this denominator. Therefore, the integral of x to the 4 over x minus 1 dx is the same as the integral of x cubed plus x squared plus x plus 1 plus 1 over x minus 1 dx. Something smells a little off there, doesn't it? Is that supposed to be tuna?
Yeah.
I would call them up and complain. Yeah, that looks like ass. Did they really charge you for that?
Yeah.
And it really smells that bad?
Yeah.
And it's really supposed to be tuna?
Yeah.
Sorry, we just got some rank ass sushi delivered here. I don't know what the fuck this restaurant was thinking, but goddamn. Anyway, this long division tells me this function is equal to this polynomial plus this rational piece. Since this rational piece is actually so nice, I don't even need to do any PFD. We're good to go. We can just integrate this. X cubed becomes x to the 4 over 4, plus x squared becomes x cubed over 3, plus x becomes x squared over 2, plus 1 becomes x, and then I have plus integral 1 over x minus 1 dx. My phone? I'm not sure where it is. So oh, here. No, you did. Yeah, they should give you your money back. And then this guy is the little micro u sub. We let z be x minus 1, dz is dx. So this piece becomes integral 1 over z dz. So he'll become a natural log. And at the end of the day, we get x to the 4 over 4 plus x cubed over 3 plus x squared over 2 plus x plus the natural log of absolute x minus 1 plus c. So yeah, it's the long division that makes the magic go here. That's a good question. I'm not sure where we ordered this from. Yeah, I genuinely don't know. I mean, we've ordered sushi from a bunch of different places. I've been busy working. My wife ordered it just a bit ago, so probably somebody on Bite Squad. But I'll let you know next time if you want to know. Liquid ginger is good. I like liquid ginger a lot. Yeah. Other place I've had really good sushi in town is Sushi Matsuri. So we want to go over the long division a little slower. I wasn't going to say anything, you know, if you like bento, you like bento. There's nothing wrong with that, and I think they probably do some things well, but I wouldn't go there for good sushi. But to each their own. If you enjoy it, it's good food for you. The first part here was long dividing this top by this bottom. To do that, I wrote x to the 4 as x to the 4 plus 0x cubed plus 0x squared plus 0x plus 0. So this is my numerator, just written out in standard polynomial form with all the missing terms inserted. And over here I write my denominator, the thing I'm trying to divide by. To do the actual division, we pay attention just to the lead terms. So to get this x cubed, I ask, by what must I multiply this x in order to get this x to the 4? And the answer is x cubed, right? X cubed times x is x to the 4. Then I distribute this x cubed over this whole term, getting me x to the 4 minus x cubed. And then I subtract this whole row from this whole row. And that gives me this. And then I rinse and repeat. So what must I multiply x by in order to get x cubed? Well, that's x squared. Then I distribute this and I write that here. And then I subtract this whole row from this whole row. And we keep going like that until we get to something whose degree is strictly less than this. Then at the end, this is what goes upstairs. So you'll have your polynomial piece. This piece goes here. And then you'll have your remainder term over your divisor. So this is something that is supposed to be covered in 1140 and 1147, dividing polynomials and rewriting a quotient rewriting a ratio as a quotient plus a remainder. But I know that it's not always covered very well, so I will try to post something in the Canvas modules about this, dividing polynomial stuff. All right, I think that's where we have to end it. I do have an office hour coming up, so if there's anything that you guys want to talk about in office hours, I invite you to come by. Remember, I really want to discuss your study guide problems with you. I want to see what you're writing down, and I want that to happen before the exam. That way I can give you some meaningful feedback on your work before I actually have to grade it for a test. So if you want to do that, come by an office hour, or scan and send me your work, or just send me a little picture, anything, just so I can see some of your work and we can chat about it a little bit. If the office hour is not convenient for you, send me a message on Canvas. I'd be happy to set one up anytime tomorrow or Thursday, except between like 4:30 and 6 tomorrow because I have a doctor's appointment. But really any other time tomorrow I can meet to talk about study guide problems. I would love to meet with you and see your work so I can give you some pointers, and that way you're not surprised by any of my grading on the test. Remember to get homework 5 knocked out, get the study guide knocked out. Remember, you need to scan and submit your submissions to the study guide. It is not just about doing them in WebAssign. Please read the Canvas announcement for those details. It's very important. And if you haven't yet, also run through the practice quiz with HonorLock. There's no questions, so you don't need to feel any pressure. It's just about making sure your computer can run through the HonorLock stuff. Okay, so I'm going to go ahead and end today's meeting here. And if you guys want to continue any of these conversations, come see me in office hours. I'm sure good sushi will be in my future at some point, if not today. So thank you for the concern. Yeah, take care, guys.